Okay, so it's my privilege to introduce the speaker today, who's done a lot of really cool work in common sense, which is a near and dear place in my heart, general learning around large language models, and we're going to hear a bunch of stuff today about how to get them to do things that they weren't trained to do. So he has had a nice career moving around from like McGill, where we have a lot of connections, over to Stanford, as well as University of Washington, like from University of Washington down to Stanford, and then AI too. Right, I got that order right. And now he's a professor in Switzerland, doing a lot of really cool work. So let's give him a little applause. And
all right, thanks for that great introduction. Yeah, so as mentioned, my name is Antoine Bosselut. I lead the NLP lab at EPFL, which is in Switzerland. There's a wonderful view of out of my window in my office. Just kidding. My office is somewhere in that picture, but that's not quite what I see on a daily basis. And I'm here today to talk to you about new ways of thinking about the information that is encoded inside large language models, the types of knowledge that they capture, and specifically how we can leverage those pre-trained representations to simulate more complex cognitive processes, such as human reasoning. So I'm going to talk a bit about two papers that we've done in the space today. And feel free to interrupt me at any point in the talk. If you have any questions, I'm happy to take questions online as we move through it. So getting started. In my research, the key question that I typically try to answer is, can we design models that represent and reason about knowledge the same way that humans do? Why would we actually want to answer this question? Because it's really the most important goal to unlock agents that can actually advise and augment our own capabilities. They need to be able to understand situations the same way that we do, so that they can provide solutions that, at worst, are what we would think of doing, and at best address our problems in more constructive ways that we wouldn't necessarily have come up with on our own. So to give you an example that I've continually used over the last few years as to how a machine should be able to think about the situations that we present them with, if I give you these three sentences: it's going to snow, it was on TV, I'll have to wake up 30 minutes earlier, you can immediately recognize that this is a very limited narrative. And yet, despite that, most of you are going to be able to make these statements coherent with respect to one another. You're able to first recognize that a lot of information is missing in this narrative that would probably help to get a more complete understanding of what's going on. You're also going to have to potentially fill in a lot of gaps for those to make sense. Once you recognize that a lot of information is missing, you're going to rely on shared intuitive inferences to establish context. So essentially bring in more information from outside that you have identified as potentially relevant from years of personal experiences. So maybe if you have children, you'll have to get them dressed for the cold, wet weather in the morning, which is going to take time. If you have a car, you'll have to clear it out of the snow, maybe heat up the windshield, get the ice off, and potentially dig it out. And finally, once you've made all these intuitive inferences, you're going to settle on a new picture of the situation based on being able to reason over these incredibly rich but unstated imagined implications. And that's what ends up making the narrative coherent for you. And for a machine to actually be able to provide a recommendation, such as the fact that you need to wake up 30 minutes earlier, it essentially needs to be able to do all of these same things: identify this information, ignore irrelevant information, bring in this outside context in order to give you the right recommendation, as opposed to, let's say, telling you that you should turn off the TV because it's giving you bad news. It needs to be able to represent and reason about this knowledge in the same way that you would want it to. So how should machines know how to do this? Ultimately, we need to be able to find some sort of alignment between how humans and machines think to do this effectively. And to do that, we need to answer a few questions. The first probably being, how do humans actually represent the knowledge that we have to be able to navigate these types of new situations? Now, if you worked in the space for how humans represent knowledge, you're going to realize that this is a problematic question to ask, because we don't really know how humans do this in the first place. What do we know about how humans represent knowledge? Well, we know that general knowledge, such as facts, is organized by what we typically call semantic memory, which is specifically related to being able to remember pieces of information such as factual information. And this is in contrast to what we call episodic memory, which we typically use to remember events and experiences that we've had over the course of our lives. Practically, though, what's interesting is that both of these memories behave quite similarly in how they're encoded in the brain. So they're typically actually both classified into another class of memory that we call declarative memory, which is defined as all sorts of memories that involve the conscious recollection of information. And what's interesting about declarative memory, beyond that breakdown that I just gave you, is how these memories end up being recalled. So when we think about memory in a computer science context, we're generally imagining that there's some sort of location where information is stored, and accessing it is all about finding out where that location is and reading that information from, let's say, memory or disk. Unfortunately, human memories aren't actually retrieved in the same classical computing sense. There's no single place that you access a memory in order to retrieve it. Instead, memories are typically reconstructed across multiple areas of your brain as you actually try to recall information. Now, what we do know is which areas of the brain are involved in this process. So, for example, there's this famous example of Henry Mollison, of whom there's a picture right here, who a long time ago had portions of his temporal lobe removed. He had this unfortunate quality where he had epileptic seizures a lot. And so when he removed part of his temporal lobe, this included his hippocampus, which stopped the epileptic seizures that he was having. But as a result, he also completely lost the ability to reconstruct memories for things that he had learned up to 1 to 2 years before he actually had this part of his brain removed. And he also became incapable of forming new memories after that fact. And so this brings up our first point about what we know about human knowledge representations, is that in general, when humans represent knowledge, they're not actually finding a single place where that information is stored and learning how to access it. Instead, there's a constructive process that retrieves and formulates those memories. So we're reconstructing the experiences that we've had before, where the information is located. And if we remove modules that enable this constructive process, we lose the ability to reconstruct memories in the first place. And so this is a bit problematic because that's not at all how we have formulated the interpretation and representation of knowledge in large-scale neural networks. In fact, when we talk about interpretability from a machine learning perspective, we're typically completely abstracting away from these processes that are actually going on in the network and really formulated it as some sort of memory access. In general, we prompt the model with a specific sequence of tokens, and this maps through some sort of process that we ignore to a specific output that is supposed to represent that the model actually understood what it was being asked. Essentially, the question that's being answered is, what knowledge can this language model directly express when it is prompted for that information? So Pretrained et al. 2019 were some of the first to actually bring forth their perspective, where they defined prompts for different triplets in knowledge graphs. So they would go from a knowledge graph of cafe with a relation ISA and a tail entity restaurant, verbalize that into some sort of prompt, remove the ending of that prompt, and then ask the language model to fill that prompt or complete that sequence in order to reflect that it actually had the information that was needed to be able to understand this sentence. In other words, access the knowledge that was involved. Another class of interpretability methods beyond prompting are what's called probing, which rather than ask whether or not a piece of knowledge can be expressed, pretty much asks whether a piece of knowledge can be extracted from the representations of the language model. So if you take, let's say, a vector output of that model at some point in time, or at some intermediate state of the network, can you train some sort of simple classifier using that representation as input features to extract some understanding of the sequence that has been given to the model at that point? And then finally, there's a new class of methods that are generally called mechanistic interpretability methods, which explore the question, how do expressions of knowledge change when we apply certain interventions to them? So that might be, let's say, masking out certain neurons in the network, removing certain layers, and seeing what effect that has on what types of outputs our model gives us when we provide it with certain inputs. But so each of these methods typically has a long list of shortcomings. And the main one in general is that most of these methods, whether it's prompting, probing, or these types of mechanistic interpretability methods, such as model editing and causal interventions, completely ignore how knowledge is reconstructed by the model when it is output in the first place, in order to just try and figure out whether that knowledge can be extracted or expressed in some way. And that's not necessarily how humans end up representing knowledge, which causes this divide between the interpretability methods that we have for understanding the knowledge and systems in a machine learning context, and the ones that we actually know about from a human perspective. And we actually see a very similar divide in how we think about human reasoning. So if I ask you how you think humans reason about knowledge, well, the sad truth here is that we also don't really know how humans reason about knowledge. There's lots of theories. I'm sure most of you know about this very recent famous one of System 1 and System 2 reasoning. That's one take on a human reasoning process. There's countless others out there. One that I actually particularly identify with was outlined very nicely in this book by Hugo Mercier and Dan Sperber a few years back, based off some initial explorations by Evans and Watson in the 70s, that essentially says that humans mainly reason to justify the intuitive inferences that they make at any particular moment. When we actually make decisions or make predictions, we kind of make them on the spot. There's some internal processes that drive that decision, but it's very much based off intuition. And then reasoning actually comes into play when we need to justify ourselves to others. We can't really just say that we disagree with someone because we think so. We need to be able to provide reasons for them. And so when we evaluate the arguments of others, and specifically when we justify our own decisions to other people, is when we typically do this conscious act of reasoning, as opposed to having it be an internalized system that we do naturally. And so reasoning then becomes most effective as a retrospective act of justification, as opposed to some prospective act of inquiry. If you're interested in this, I encourage you to read more into this concepts. Ultimately, a big part of why this hypothesis is the case is that humans are actually super bad at using reasoning in a personal way through things like confirmation bias. We typically come up with bad ideas all the time, but we think we're right, and we only realize they're bad when other people tell them that they're bad. So why is this perspective on reasoning as a tool for justification important? It's important because it's also exactly what we do when we learn. We don't necessarily evaluate arguments and reasons that others give us, but when we learn, but we often evaluate our observations about the world according to some world model that we have already constructed from experiences. So John Piaget, in his theories of cognitive development, proposed that we generally use two processes when we're learning from our environment. The first is what's called assimilation, which is where we fit the observations that we make about the world to our existing world models. And the second is accommodation, where we learn how to change the world model to accommodate the observations that we're seeing in the world. And ultimately, if we're to use reasoning effectively, what's important is that this has to involve both assimilation of new knowledge and the accommodation of world models to the observations that we see. Or else we're not actually truly doing reasoning, we're not truly doing learning, we're essentially just doing assimilation, where we try to adapt what we see to what we already know. This is how language models reason about knowledge. Well, we also don't really know how they do that. But in general, when we look at the different ways in which we design language models to do reasoning, I'm going to give you a very simplistic view of it here, that we generally have two approaches. The first is what I like to call the what do you think approach, which is we ask the model what it thinks. Chain of thought prompting is one way of doing this, where we tell it to think step by step and just tell us what it thinks about a particular problem that we give it. The second is what I like to call the think like this approach, which is we might give it some sort of symbolic structure, like a knowledge graph or a first order logic, and essentially give it the scaffold by which it could do reasoning. But it's ultimately stuck using the tools that we provide to it, either the ones that it has already learned from pre-training or the ones that we give it as part of the input that it can learn to use. In both of these cases, I'm going to tell you that reasoning is purely assimilative. Essentially, the world model that the model can use for reasoning is already established and cannot change. And essentially, you are only just fitting the model's observations to what it has learned before. So what I'm going to talk about today is how we can learn to identify knowledge representations and reason about provided knowledge more similarly to how humans do these two things. So in the first part of the talk, I'll talk about how we can localize the constructive processes that language models use to reconstruct memories and that are responsible for being able to encode particular types of knowledge. And then in the second part of the talk, I'll talk about a new reasoning method that we've designed that specifically learns to reason by assimilating new knowledge and accommodating the parameters of the network to be able to change the model's internal world model to accommodate that knowledge in the first place. So diving in, the first paper I'm going to talk today is one that was on arXiv that a few people have brought up to me already. So thanks for reading. Called Discovering Knowledge Critical Subnetworks in Pre-trained Language Models. This is work by my student Dennis, along with Nagar and Eric, and my postdoc Gail. I did a bit of work on it as well, very few though. But essentially, this paper tries to answer the questions of how we can identify the mechanisms that reconstruct knowledge that is encoded by the model. So moving away from the fact that model information should be accessed and more thinking about the constructive process that reconstructs those memories that the model has. And we talked a bit about what are the shortcomings with how classical interpretability methods try to attack this problem. So issues with prompting, probing, model editing. Our take on it is that in order to actually reconstruct the knowledge that this model encodes about these concepts, you need to identify a subnetwork within the model that represents the process by which that information is reconstructed, not just try to find it at a particular point in the network. And so we define this concept of a knowledge critical subnetwork, which is a subnetwork within the model that is responsible for that process by which a piece of knowledge is reconstructed. And mechanistically, how do we define this knowledge critical subnetwork? Well, essentially according to two properties. The first is suppression, is that if we were to remove this subnetwork from the larger model, then the knowledge that that subnetwork reconstructs should no longer be able to be expressed by this model. So in other words, it should be removed. So more specifically, if we have a set of knowledge that we're going to call target KG, so a target graph of knowledge, which is on the left here, we're going to try to find a way to snip this network in the middle here, such that when we remove that subnetwork from the model, it should no longer make the same predictions about what the knowledge that follows that particular prompt actually is. In other words, for a prompt such as a cafe is a type of blank, we should see a drop in likelihood on what the correct token that finishes that prompt actually is. And the second property that we want to ensure is what we call maintenance, which is that we should want the remaining behaviors of the model that are outside of that reconstructed process to essentially remain untouched as we search for the subnetwork. So if I were to prompt the model for a different piece of knowledge that's not a cafe as a type of restaurant, and instead it's a car as a type of vehicle, the distribution over what the model knows about the sequence should remain roughly the same. And so here we define a control knowledge graph that contains knowledge that should not change as a result of this information. Yeah.
So you may be about to answer this. When you're trying to keep knowledge around, this is the stuff you have in blue here. Are you trying to keep around all the knowledge about restaurants, all the knowledge about cafes? If you keep both of those, then you would probably know that a cafe is a type of restaurant because you know the things that go on in cafes and things that go on in restaurants. So what's the mutatis mutandis?
So in general, in the way that we've defined the experiment, when we build the target KGs, we specifically look at neighborhoods of a seed entity. So we'll find, let's say, cafe, and then we will do 2 or 3 hops away from that entity within the knowledge graph to find what the target knowledge that should be removed is. So we're really removing knowledge families at this point. Then for the control KGs, we do another hop. We don't do anything with those nodes. One more, and then everything that's one more hop outside of that, we put in the control KG. So there is this bit of this gray area, let's call it no man's land, of whether something should be removed or not, depending on whether it's one hop away from the last target KG.
Cafe, not away from restaurant. Is that right?
So because restaurant is one hop away from cafe originally, there's going to be plenty of knowledge about restaurants that are in the target KG. So in fact, everything about restaurants should be removed because it's one hop away. So yeah, there's definitely a question of precision that comes into play of how precisely you can target particular modes of knowledge. We can talk about it later, but that question actually becomes philosophical after a certain point of what can remain the same and what cannot remain the same when certain facts become removed. And then the last thing we want to make sure of is that we also retain all of the other abilities of this language model that don't nicely come down to describing knowledge. Ultimately, these language models are very rich tools. They should be able to do everything else they once knew how to do. And we regularize for that by having this control LM, which is a bunch of other random sequences that don't necessarily describe declarative knowledge, should also remain in this system. So now that I've told you that we're looking for this reconstructed process, how do we actually discover the subnetworks or circuits within the larger model that represent these processes? So what we're going to do is use a class of methods called differentiable weight masking, which is that essentially what you do is that you assign some sort of mask parameter to each weight in your network. And then you learn a binary value for each of those mask parameters that's multiplied by the weight that used to be in the network. Essentially, this masks the weight if it's 0 and keeps it in the network if it's 1. And the effect of a masked weight is that it is effectively removed from the system since it can no longer contribute to any input that is provided and leaves you with a subnetwork of the original system based off the masks that you have actually learned. So to learn these masked weights, we're going to do a slight modification to some methods that already exist from before. Bengio et al.'s work in 2013, and Zhang et al. And Madison's et al.'s work from 2017, where we define some learnable parameter for each one of these weights, which we call Li in this framework. And then for each of these parameters, we're going to compute a weight-specific score, SI, and use what's called a straight-through estimator to map that score to a binary value, MI. So a straight-through estimator essentially works by forcing SI to 0 or 1, depending on whether or not it is below or above a certain threshold, which in this case, we set to 0.5. So if SI is greater than 0.5, then this I value becomes 1. You subtract SI, you add SI, it becomes 1. If SI is less than 0.5, that's 0. You get negative SI, you add SI, it becomes 0. But the benefit is that because this part is detached here, but you have this plus SI, you can directly backpropagate gradients with respect to what happens above in the network, such that you are able to change the SIs to better model the task that you're trying to do at the output. And then to stabilize learning and not get stuck in a local minima in the process, you also have this noise term when you compute the SIs along the way. And finally, we also have this regularization term that encourages the model to be as sparse as possible. Essentially, as long as you're reconstructing the subnetwork that you want the mask parameters to essentially be as close to 0 as possible, so that you're coming up with the sparsest subnetwork that you can imagine that completes the task that you're trying to do. So this is the process that we actually use to learn a mask over the network that represents these subnetworks that are knowledge critical. And so with our original goals in mind, we're going to define 4 terms for this loss function that we optimize to be able to learn this mask. So to start, at each step, we are going to have a current version of our mask over the whole network. And we are going to also have an unmasked portion of the network that we call the remaining model. So once we discover the subnetworks, the remaining model is what is left when, if we were to remove that subnetwork, it's the unmasked portion of the network. And first, to be able to remove the knowledge that's in the target KG, we're going to try and minimize the KL divergence between the remaining model's distribution and some sort of uniform distribution. Essentially, that is what our proxy is for this model having no more clue at all about the knowledge that is represented in target KG. We tried varying forms of this, but this one seemed to work pretty well. Another easy idea that folks often have is to just set it to 0. So the value on the knowledge they're trying to represent should be 0. That's actually very difficult to do because knowing absolutely nothing about a concept such that there's 0 probability actually requires a whole lot of knowledge about everything else. So it actually ends up being very difficult to find a sparse subnetwork if you do that. But essentially, you're trying to find some sort of objective such that the model has no idea how it should complete the prompt, and a uniform distribution is a pretty good way of doing that. And then for the control elements, we're going to define 2 loss terms. The first is both times minimizing some sort of KL divergence between the original model's distribution and the remaining model's distribution. So for control KG and control LM, whichever sequences we're using to model those control states, we're essentially going to try and make sure that whatever the remaining model thinks about these sequences looks roughly similar to what the original model did. So it shouldn't actually affect how the remaining model thinks about these concepts. And then finally, as I mentioned, we have the sparsity regularization term. So your model should try to discover the sparsest subnetworks that it can in order to find in order to represent the process by which you reconstruct these knowledge critical components. So, and that's pretty much it for yeah.
A question about the loss. So with the suppression loss to uniform, so you cannot guarantee that argmax will not give you the restaurant in the previous example, right?
No. You can't guarantee that the argmax wouldn't give you that answer.
Are there ways to get at that in a more hard constraint fashion, or just very different?
Yeah, so what you could potentially try to do actually, and there's some works that do this for, let's say, trying to remove private information from language models, that you could actually use gradient ascent on the fact that you try to represent. And that way, rather than learning that fact, you try to unlearn it. Now, typically, there, I mean, I would say you should probably actually cap the maximum loss to which you can ascend by whatever the uniform distribution would give you, because or else it actually starts requiring a lot of capacity to learn something towards zero. But you could potentially try to make it a bit above the uniform distribution so that you find a balance and it's no longer the argmax. But in general, I guess we don't necessarily measure this in a generation setting after. We're going to mainly look at perplexities to see whether this knowledge is unlearned. However, what I can say is that oftentimes the ending of the prompt is not actually the argmax token that you would have necessarily gotten. You would have, let's say, another continuation that is more that the model originally has a higher probability on compared to the group tree. Yeah, questions?
So just to make sure I'm following the notation here, these are actually conditional Cal divergences, and you're sitting in the first case on a cafe as a type of, and in the second case in a car as a type of.
Exactly. Yeah. So you're essentially taking it's the Cal divergence on the last token, on what the model thinks the distribution over the last token should be in the prompt.
One more question. Just one token at a time.
Well, in this case, we only ever try to look at the last token. So we assume that the head token and the relation are always given, and we're only looking at the last token.
So one question about the uniform distribution again. Not knowing a particular target knowledge is not the same thing as uniform, right? Because after all, what I'm thinking is there might be a set of plausible things, and uniform over that is more representative of not knowing what a cafe is. And for example, one might know what a cafe isn't without knowing what a cafe is.
Yes.
I'm wondering whether because what I'm thinking is the choice of uniform in the first loss is pretty bad for any other things that involve similar contexts, and you don't want to change those. So
yeah, so I guess the question is, if you know that specifically there are words that should not be the ending of the prompt, right now you're essentially putting those to the same probability mass as the ones that were originally there. Yeah, that is a shortcoming of using a uniform distribution in this setting. In the way that we designed the work, we were specifically trying to remove the understanding of what are the target words. So essentially lobotomize any understanding of cafes. When in fact, knowing that a cafe isn't a chair is perhaps also a piece of knowledge that you might want to retain. That could be an extension of
what
the
I'm
work.
thinking, for example, is that instead of uniform, is there some proxy like a context independent distribution on the next word? And things like that. Or I'm even thinking of simple things like just the frequency of words in the language. There's no reason to ignore that.
Right. So if you're thinking that it just is a type of, and it's not a cafe is a type of, it's actually the type of.
X, if I said X,
And so you still focus on that.
Yeah. So there's probably definitely other other distributions that you could use as the reference distributions in either the suppression term or even the maintenance terms. The uniform distribution ended up working pretty well.
No,
we did it.
I'm not so interested in the mechanics as in the philosophy. What would be considered not knowing something?
No, I mean, that's a good question. So we did try something similar originally, which was you take that last word and you just set that one to random, but then you redistribute the mass proportionally to all of the other tokens in the vocabulary. The challenge there is that it becomes a tougher learning problem because actually your model is going to be doing pretty well at the start of minimizing that divergence, because in fact there's barely any divergence. It's just one bit of mass on one token that now needs to change. This creates kind of enough of a driver to actually optimize that you end up getting something by the end of it. But yes, I agree that whatever subnetwork you are discovering is one that has very broad knowledge about cafes at this point, as opposed to just the fact that it's a restaurant. So you're removing more than just that very simple basic fact in the way it was expressed. These are, I think we'll keep coming back to the fact that there's a lot of philosophical questions about what it means to represent knowledge as sequences and how, we remove what is a broad set of knowledge through just the optimization on a particular sequence. So yeah, as a quick synopsis, in general, we're defining these knowledge critical subnetworks as being responsible for encoding the constructive process by which this knowledge is expressed. And we do this by learning a sparse mask over the parameters of the network. And we specifically optimize that mask such that when the subnetwork is removed from the model, that knowledge is no longer encoded by the system. So it can no longer be expressed confidently. And then finally, we have some regularization so that the other behaviors remain relatively unchanged. And as we talked about before, we're essentially going to take two knowledge graphs, WordNet and ConceptNet. To do this, we're going to identify a set of target KGs by sampling entities in that graph, and then essentially doing a multi-hop expansion of the graph. And then we essentially take control KG as what is outside target KG, and then one more hop away. So there's definitely this gray zone in terms of knowledge that's not controlled for nor removed. Specifically so that we can, I guess, avoid the very tough task of defining how much, how many other facts should also be removed if the model no longer understands, let's say, that cafe is a restaurant. Does that mean that it also, if it's all the way at the tip, does it also not know that restaurants serve food, that they typically employ waiters and waitresses, things like that. And then finally, control LM is just Wikitext2, which we use for that control state. In terms of how we're going to evaluate this, so if you recall, we defined these three criteria for identifying a knowledge critical subnetwork: suppression, maintenance, sparsity. And so to measure whether these goals are achieved, we're going to define this metric called delta perplexity, which is the difference between the perplexity of the remaining model relative to the target or maintenance knowledge and the perplexity of the original model on that same knowledge. And in general, what we want to see is that the change in perplexity on the target knowledge is very high, indicating that the model has become a lot less confident about the completions of the target knowledge prompts. In other words, that knowledge has been suppressed. And then for the control data sets, we essentially want to see that the delta perplexity is close to zero, because that means that it's maintained its exact same confidence on these pieces of knowledge. And then finally, we want the sparsity to be high because we really want these subnetworks to be as small as possible. So the first question that we asked ourselves is, can we actually discover these knowledge critical subnetworks? And the answer here is yes. So we ran this study on multiple GPT-2 size models. And when we look at the subnetworks that are discovered using our method versus subnetworks that are found by randomly masking at the same sparsity throughout the original model, what we find is that there's a drastic difference in perplexity between the remaining models on the target knowledge. So that delta perplexity is close to 600 on the target knowledge, while it's 21 if you use a random subnetwork that you remove instead at the same sparsity level. However, if you look at what happens on the control side, you can see that the delta perplexity is roughly the same for the control KG as it was for the target KG for a model that has a random subnetwork at the same sparsity removed, while it is much less for our knowledge critical subnetworks, which actually is able to maintain the rest of the behaviors of the system. And this is a pattern that holds across multiple different model scales. So when we use GPT-2 medium instead, we see the same patterns emerge. And when we use GPT-2 large, we in fact see an amplification of those patterns. Essentially, if you remove a random subnetwork, you barely change the system. And as you remove a knowledge critical subnetwork, you see much larger gains in delta perplexity compared to before. And you still, however, you still maintain a fairly controlled, you still maintain the delta perplexities on control KG and control LM close to zero. A fun pattern to, I guess, justify a bit that these are actually the knowledge critical subnetworks is that we wanted to make sure that we hadn't just completely overfit and found some subnetwork in parameter space that happened to no longer encode this type of knowledge. If we start removing more knowledge from this remaining model afterwards, what we see is that the delta perplexity remains high. So in other words, if we had just completely overfit on this to a model that just no longer had that knowledge, we would expect that to go back down towards zero afterwards. Instead, it remains pretty high. Meanwhile, if we add parameters back in, and until the sparsity is roughly zero at that point, we see that the delta perplexity drops until it reaches the original model performance. So what we take from this is that the knowledge is actually really gone if we remove the subnetwork that represents the process by which that knowledge is normally reconstructed. A fun philosophical question that we asked as well is the ability to express knowledge the same thing as being knowledge critical in the first place? And here, what we found that was interesting is that that's actually not quite true. So, if we ask, are knowledge expressing subnetworks the same as knowledge critical subnetworks? We find that they actually don't tend to be. So we define knowledge expressing subnetworks as one that essentially just tried to maximize the likelihood of the target knowledge that we see. So find a subnetwork that essentially maximizes the probability of that final token in the goal target knowledge. What was interesting is that when we removed these subnetworks, it actually did kind of follow the properties that we wanted. So if we remove, let's say, a very sparse subnetwork that's just very good at expressing the sentence, a cafe is a type of restaurant, what we find is that the delta perplexity on the target knowledge actually jumps by around 154 points, which in this case was kind of a doubling factor. So removing some subnetwork that we find that just is really good, gives a high probability to a cafe as a restaurant. When we remove that, the rest of the model has trouble expressing a cafe as a restaurant. However, what we also found is that it also drastically increased the control KG perplexity. So what we believe is that, in general, we were removing parameters that are useful for expressing all forms of knowledge, as opposed to just the target knowledge that we wanted. So given this, we also have this natural idea, well, why don't we try to combine them into a single objective? And this actually, seems to fix this issue where, in fact, if we combine them together, we get a much higher target KG delta perplexity, around 909, much lower control KG delta perplexities, and it seems to fix the problem. However, we also find that this subnetwork is much less sparse on average. And in fact, it is less sparse than the union of the expression only and knowledge critical methods that we have. And so, our hypothesis for this is that joint objective cannot actually discover the true constructive process by which the target knowledge is reconstructed, because there's competing influences. Essentially, to find a subnetwork that can express the target knowledge very well, you're also going to find subnetworks that express the control KG knowledge very well. And so if you try to remove the expression only subnetwork of the expression term, it's actually almost impossible to regularize for control KG. In other words, this is a massively overfit network at the bottom there, which is why it ends up being incredibly less sparse than the ones that we were able to find without the joint objective. Yeah.
I'm wondering with the sparsity kind of baseline, the random one, if you instead got rid of just suppression, it kind of trained it still with the same regularizer to do sparsity, do you think you would get kind of a different sort of threshold there? So maybe you would still have a lot of general knowledge, but a much smaller network. And it's not randomly, there's been over parameterized.
Well, so you need the suppression term to find the you mean so
Yeah,
assuming you have the expression term.
Yeah, I think you still have an expression. Yeah, that's what I'm wondering there. So
that's a good question. We have an ablation study in our work that essentially looks at what happens when you remove different terms of loss, and the suppression one is actually pretty critical towards having the knowledge critical one. The thing about it is that, well, so I guess to give a high end is if you do expression only, we were actually surprised by this result, because you can typically find any group of parameters that can express any piece of knowledge within that model. And so just because you're able to express the knowledge with that subnetwork doesn't mean that that is the subnetwork that the full model uses to express that knowledge normally. It can just be a spurious set of parameters. And so then finally, the thing we asked is, okay, so if these are knowledge critical subnetworks, then they should have a broader impact on the model than just the inability to remove this knowledge. And so we asked whether they could be useful for downstream transfer. And what was interesting is that this was actually the case. So when we build target KGs by identifying triplets in ConceptNet that were relevant to test set questions in Common Sense QA, and then we discovered knowledge critical subnetworks associated with those triplets, removed those subnetworks, and then trained a GPT-2 model on Common Sense QA, what we found is that depending on what the fine-tuning procedure that we had was, we would see a major drop on the model's ability to transfer to the test set. So if we removed the knowledge associated with the test set questions from the network, the performance of head tuning, which is a pretty basic fine-tuning method, only tune a layer on top of the pre-trained language model, essentially drops to random performance, while fine-tuning with a random subnetwork stays close to the same performance as fine-tuning with the full model. And we can see that there's no similar impact on the dev set. There it stays similar as well. So it's only on the test set, which has examples for which you have removed these examples and the knowledge associated with those examples. And while head tuning is a pretty basic fine tuning approach, we also see a similar pattern with LoRa, where we tend to see a performance drop. But as you make that fine tuning method more expressive by allowing more parameters to change, in general, the model is able to rewire itself to recover certain connections that it needs in order to make those predictions. So some quick takeaways here. The first is that we're able to discover these knowledge critical subnetworks across model scales. The second is that knowledge criticality and knowledge expression are not exactly the same. And the last point, which I think is the most important, is that removing these knowledge critical subnetworks reduces the transferability, and the extent depends on the expressivity of a fine tuning method. So if somebody has access to a full model and can do full fine tuning, maybe not all that useful. However, if you're going to be deploying one of these models as a black box, perhaps it is quite helpful to be able to remove how that model is able to express knowledge in the first place. So now that we've talked about, how we can kind of change the way the model reconstructs knowledge, let's talk about the reverse, how we might change how the model learns how to reason about knowledge that it has in the first place. And so we had this work that is going to be published at NeurIPS this year called Reckoning. That's about reasoning by updating the implicit world models that the model has. This is work by my student Zemming, who goes by Eric, Gail, and then Eric and Asli, who are from Stanford and Meta. And our goal with this project was to create reasoning systems that are capable of not just the assimilation of knowledge, which is what I describe most language models are doing, learning how to interpret their observations to fit with the world model they have previously learned, but also accommodating their world model to accept the new forms of world knowledge that they receive. Kind of putting this at a low level, essentially, most models these days are doing what I like to call in-context reasoning. They might receive some sort of knowledge. They might receive some question that requires that knowledge to be answered. They pass it to an LM that has a static, frozen form of parametric knowledge that they've learned from pre-training, and then they provide some sort of answer. Chain of thought reasoning also works this way, where essentially, even though you're generating the knowledge that you need to actually do the reasoning process to arrive at the answer, it's still only assimilative in that the world model of that language model remains the same. Its parameters remain static. So the question we're trying to answer is, how can we actually design reasoning systems that modify the world models as well? And this is a really challenging problem because when we start thinking about allowing models to change their parameters, change what they know about the world as they receive new information, you start to realize that that's not necessarily something you may want to do. Ultimately, real world expressions of knowledge tend to contain a lot of noise. LLMs are sensitive to that noise, and you may end up in situations where your contextual information disagrees with, let's say, static representations you've already learned. So it's actually quite complicated to understand what type of knowledge you should assimilate. So in other words, interpret in such a way that it fits with what you already know, and which types of knowledge you should accommodate. So change what you think you know so that it makes more sense. And so our approach to do this was to actually have the model learn the knowledge in real time when it is presented with it, so that at a later point, it could answer any question that required that knowledge. And so the reasoning becomes part of the learning process to encode that knowledge into the parameters of the system. So it's kind of a quick comparison to what it looked like before. In a typical system before, you get your contextual knowledge, get your question, do a forward pass through the model, get your answer. Now, you're going to encode that contextual knowledge into the parameters of the system. And then later on, at any point, I can give you a question, and you're going to be able to answer that question in real time. So how are we going to be able to do this? So we're going to do a twist on a method called model agnostic meta learning, or MAML. How many folks here are familiar with MAML? Okay, so a fair number. Pretty much classically, MAML is a method for few-shot learning. Essentially, in MAML, you learn how to adapt the parameters of the network quite rapidly, so that when you're given a few training examples of a new task, you can quickly learn from those examples how to predict that class to do the task later on. So for example, I would want to learn some set of initial parameters such that if I got one example of a banana, a cat, and a dog, I could afterwards classify a bunch of examples of bananas, cats, and dogs. But I would be learning how to classify that from something that was not exactly the task that I've been doing up until this point, which is something that deep learning is typically kind of bad at. How do you typically do this? Well, in MAML, what you typically try to do is well, you can learn many different things, but one classic way of doing it is try to learn an initial set of parameters such that when you learn from those training examples, you can now do the new task that you want. So typically you'll have an initial set of training examples, which are often called the support set, and you try to learn from those training examples such that you update the parameters of your system, such that when you see a query set of examples, you're able to classify those examples correctly. And importantly, what you want to do is find the initial meta parameters that minimize that test loss over many tasks. Kind of, making it super simple since we want to go fast. What you're trying to do in meta learning is learn an initial set of parameters such that when you take a limited number of gradient steps on some new training examples, you adapt the model to be able to do the task that is represented by those training examples. So you're trying to find an initialization for your model that enables rapid adaptation to new examples. And so this is the general framework for MAML. You start with an initial set of parameters. You receive a support set of training examples. You change your parameters as a result of that support set. And then you can essentially classify the examples in a query set and then learn how to initialize that initial set of parameters such that you can do this effectively. But one thing that we found interesting about this is that there's nothing that actually says that what the examples in your support set are and what the tasks that you do on the examples in your support set has to be the same as the one that you're doing for your query set afterwards. In other words, you could learn how to do some sort of task in your query set that allows you to do a completely different task on your query set afterwards. And that's exactly what we exploited for our method reckoning, where we learned with our support set, so in the inner loop of this meta learning algorithm, how to encode contextual knowledge, represented through some sort of language modeling objective, such that in the outer loop, so the query set could be a set of questions about that knowledge. And those questions could be answered using the information that we had encoded in the inner loop without ever actually seeing that same knowledge once we ask the questions afterwards. So more formally, to reason about a particular problem, we're going to give the model a set of relevant facts K, a question X, and an answer to that question Y. And in the inner loop, we're going to use a causal language modeling objective to essentially encode the expressions of those facts into the systems. So essentially, we're encoding the knowledge through simple backpropagation on language modeling. And then in the outer loop, we'll use these new updated parameters that we got from encoding these facts, and we're going to compute two losses. The first, we're going to compute the model's ability to answer the actual questions with the new parameters from training, after we've done the inner loop training. And the second is that we are going to train the model to recall the facts that it has used in order to be able to answer that question. So that way, if I give a bunch of facts, many of which are irrelevant to actually answering the question, it has to tell me which facts it actually used to be able to answer this question. And we're going to compute gradients for these losses with respect to the original parameters of the system. And that way, we're going to be able to learn some initialization of the parameters such that it can rapidly learn from receiving sequences of text that represent facts, and then use those facts when we ask it to answer questions later on. So I'm running a bit low on time. So in general, we use three data sets to evaluate this, two of which I'll talk about today. The first is clutter SG, which essentially provides facts in terms of family relationships between different entities. And the second is Proofwriter, which provides facts that are like the bear eats the cow, the dog is kind, and then rules on how to compose those facts, such that when you're asked a question from these facts and rules, such as can we conclude that the bear is kind, you can compose the initial facts, you can compose the rules that you're given to actually answer whether it's true or false. What's interesting about Proofwriter is that because you often have multiple questions, many of these facts and rules will be distractors for many of the questions that you see. So the first question we asked is, using this method, can we actually reason by dynamically encoding knowledge into the model? And the answer here is yes. When we compare it to an in-context reasoning baseline using GPT-2, what we see is that generally we get the same performance using reckoning compared to using an in-context reasoning baseline. So even though we no longer have access to the knowledge once we ask the question, it has been encoded successfully into the parameters of the system such that it can answer that question in a closed book way. Now, what's interesting is that as we start moving into larger hop settings, so we actually need to do 6 reasoning steps or so in order to answer the question, it becomes more effective to encode that knowledge into the parameters of the system, as opposed to just relying on the forward pass of the neural network to answer the question. This is also true in a generalization setting. So if we only train on 2-hop questions or 4-hop questions or 6-hop questions, but then test on up to 10 hops, in general, we see larger gaps as we increase the number of hops in our evaluation sets. So we're actually able to generalize to longer reasoning chains using this reckoning method, as opposed to what we can do from just providing this information in the context. Importantly, as I mentioned, in some of these data sets, a lot of the facts aren't actually relevant to being able to answer a question. So these previous results were when all of the facts are relevant without any distractors. If we add distractors, these gaps become even more substantial. So all of a sudden, we're seeing fairly large gaps between the performance of the in-context reasoning baseline, which receives all of this information as part of the context, and our reckoning method, which encodes it into the parameters. If we have lots of distractors, we can often see differences of 10 to 15% in performance when it comes time to answer questions after. In other words, aggregating the information in the parameters of the system and learning how to decompose it over the course of this meta-learning algorithm allows you to more robustly then answer questions afterwards, as opposed to just having it be part of the context. And a big reason for this is actually this knowledge reconstruction loss. So essentially, when we look at how well an in-context reasoning baseline versus our reckoning method can recall the knowledge that it uses to answer a particular question, our method essentially can do that roughly 75% of the time, while the in-context reasoning method can only select from its inputs which facts are actually relevant to answering a question around 50-55% of the time, depending on the number of facts that are actually given. Any questions about the robustness to distractors, the evaluation setting? Okay. One last thing that we found interesting is that there's a clear correlation as well between the multi-hop reasoning distance in the questions that you're evaluating on and the number of inner loop steps you need to take with reckoning in order to encode those facts into the system. So if you have, let's say, 2-hop questions, you don't really need to do much more than 1 inner loop step in your meta-learning training in order to actually get the answer correctly. However, if you have 6-hop questions, you actually need to take up to 4 to 6 inner loop steps to encode that knowledge in order to actually answer the question successfully at the output. So this is a correlation that we found kind of interesting, which is essentially the meta-learning algorithm follows the same complexity that the questions do that need to be answered afterwards in order to do them successfully. However, we did check whether you could answer 2-hop questions about the 6-hop questions that we had in the intermediate stages. That's not actually true. So it's not necessarily constructing the same logical forms over the course of these inner loop steps, but by the end of it, it needs a lot of inner loop steps in order to answer complex questions. Okay, so takeaways from reckoning is that in order to actually create more robust reasoning systems, you need to tie the mechanisms back to cognitive processes. You need to be able to update your world model and accommodate new information rather than just relying on how your current model has learned to encode information from pre-training for reasoning. And what this gives you is that, one, it makes you more robust to relevant content in your context. So reckoning is a lot more robust to distractors. It allows you to generalize to longer reasoning chains. So essentially, because you no longer need to rely on your attention mechanism or your forward pass to compose all of the information that you have, and you can actually encode that knowledge in the parameters of your system, you end up being able to generalize to longer reasoning arguments. You actually learn how to evaluate the relevance of facts. So that same robustness to distractors essentially means that the model is able to decide which facts are actually relevant to use for a question that's going to be asked later. What's interesting is that it doesn't have access to the question as it's encoding the facts, which means that in order for it to be robust in this way, it needs to essentially learn how to aggregate information from multiple permutations of those facts, such that it can answer a wide range of questions about different combinations of them. And finally, what's interesting is that the internal mechanics of the systems, essentially the number of inner loop steps that we do, is tied to the reasoning performance when we're actually looking at longer hop reasoning chains. And so on that note, I hope I've convinced you that a way forward for identifying the processes and language models that are useful for reconstructing knowledge and for reasoning are also the ones that are actually used by models when they're adapted to downstream tasks, showing how interpreting the information that's in these systems can help us potentially design solutions for some of the problems that we have today. And then the second part of this work, I showed you how we might learn to modify those same processes that we use to encode information in order to make models better reasoners. So in other words, how can we actually use the internal representations of the systems in order to make them to reason about situations that they haven't necessarily seen before. So that's essentially my talk. I guess to leave you with a bit of food for thought. In order to align machines and humans, particularly in a way that humans find useful, we want to make machines think similarly to the way that we do. And two things that are important for being able to do that. The first is understanding how humans represent knowledge, and making machines and showing that machines represent knowledge in a similar way. So knowledge isn't accessed, it's actually reconstructed. And in order for us to be able to change what machines understand about the world, we want to be able to localize these memories for more targeted interventions. And the second one is human reasoning naturally is tied to learning. We learn by reasoning. And so that requires allowing changes to our world model as we receive new information. And so we can't rely on models being static if we actually want to make them effective reasoning. And two directions that I outline for doing this are what I talked about today. So thanks for coming, and thanks to my group for actually doing the work behind these findings. Happy to take any questions. I think we're running a bit late, so it's also fine if there's no time, but thanks. Yeah.